Greetings everybody, so today we're going to be taking a look at the subspace topology. So let's say we already have a topological space, we'll just call it M. So this is my picture of M as a set, and we already have some topology defined in it, which is just our list of neighborhoods of M. Now often we're not interested in the whole entire set M, but we're only interested in a certain portion of M, which is some subset, which I'll call N over here. So we're only interested in this bit. And the question is, if we already worked hard enough to get a topology on M, can we borrow this topology somehow and put it on N without needing to construct some new topology from scratch again? And the answer is yes, and there's a very nice illustration of how to do that. So let's say we have our set M over here again. Now what I'm going to do is I'm going to draw some neighborhoods out in this. These probably won't be all the neighborhoods on M because of the axioms and whatnot, but just for illustration purposes, I'm just going to draw a couple of neighborhoods here. So let's say these are the neighborhoods of M. Now what we're going to do is we're going to imagine this N as being some kinds of cookie cutter or something. And what I'm going to do is I'm going to take my cookie cutter and I'm going to lay it on top of all these neighborhoods that I already have. So here's my set N over here, and what I'm going to do is I'm going to cut out all these neighborhoods and I'm going to get rid of everything that's outside of N, and I'm only going to keep the bits that are inside the N, which are, for example, this neighborhood over here and this little neighborhood up there as well. Now what we're going to prove is that if we have all the neighborhoods of M and we use that cookie cutter and we cut out all those little neighborhoods such that they intersect with N, that those resulting neighborhoods that we get in there also form a topology. So this is the intuition of what's going on over here, and this is something that's very useful to do because this allows us to borrow topologies from bigger sets that we're working with. For example, if you take a look at R, for instance, but you're only interested in R+, you can take the topology that's equipped with R, which is the standard topology, and then induce it into this R+. And what that's going to give you is what we'll call the topology of R, which is the standard topology, for instance, but we restrict it to R+. So here's my N over here, and on this N now, we have the topology tau, but restricted to N. So this is the notation that we commonly use. So let's actually write this out a little bit. We want to spell explicitly what this tau restricted to N is. So let's say M with tau, this is a topological space, and we have some subset N of M. But what we're going to define is a tau restricted to N, and what is that going to be? We're going to define this as being the set, and now in here we want a list of neighborhoods, of course. But how do we choose our neighborhoods? Well, as you can see in this picture, we take all the neighborhoods of M, which are these blacker blobs over here, and we intersect it with N. So what we're going to do is we're going to take all the neighborhoods of M, let's just call it U for instance, I intersect it with N, and I require that all these U's over here are already in my original topology. And this is how I'm going to construct my restricted topology or my subspace topology. I take every single subset that I can find in my original topology, and I just take the intersection with the set I'm restricting to, which is N in this case. Now what I've given you over here, that's just a set of subsets. In order to show that this is indeed a topology, well, we need to check the axioms. So let's go ahead and do that. So what's the first axiom? We need that the empty set and the whole entire set is in this topology. So the whole entire set is actually N in this case because that's the set we're trying to put the topology on. So we require that these two subsets are in the topology. Now in order for a subset to be in this topology, we need to be able to represent it as N intersected with some element of the original topology. So let's draw it out again. If this is my N once again, if I want this subset of N to be in the topology restricted to N, then I must be able to find some neighborhood of M, which when I intersect with N creates that subset. So there could be many different neighborhoods in the original topology that does this. For example, this one does if it's open, this one does as well. And as you can see, there's potentially many you could put on, as long as each one of these are already in your topology. So for the empty set over here, we need to find something such that when we intersect with N, recovers the empty set. Now what better choice than we have than empty set over here? An empty set, this is definitely an element of the original topology. So that works. So this implies that empty set is in the topology restricted to N. That's nice. Now how about this N over here? Well, we need something such that when we intersect with n, this recovers the n. Now the question is, what could we have over here? Well, if this is n, in order for the intersection of some neighborhood and this n to be equal to n, it must be bigger than n. So we need to find some neighborhood u that's bigger than n. Now what do we definitely know? We definitely know that m is bigger than n. And since m is an element of the original topology, what better choice than we have than to put m over here? So we found a subset m such that when we intersect with n, it gives us n. And this tells us that n is in the topology restricted to n. So the first axiom is true. So let's check the second axiom. So what does the second axiom say? It says that if we have two sets, let's say A and B, for instance, so A and B are in the topology but restricted to n, then this implies that the intersection must also be in the topology restricted to n. Now we want to show that this is indeed true. Now let's start on the left hand side. If A and B are in the topology but restricted to n, then there must exist subsets u and v in the original topology, such that when I take u and I intersect with n, I recover my A. And also when I take a v and I intersect it with my n, I get my B. So here is my n. So let's say we have some neighborhood A and some neighborhood B. If A is a neighborhood, then by our construction, we must be able to find some subset u over here, such that u intersects gives us A, and we must be able to find some other neighborhood v, such that v intersects and recovers our B. But u and v, those are elements of the original topology. And if u and v are elements of the original topology, then the intersection over here must also be an element of the original topology. And from this picture, you can see that since this set over here is neighborhood of the original topology, when we intersect it with n, we also recover the intersection between A and B. So if we were to write this all out, what we could do now is take A and intersect it with B, and notice that this becomes u intersected with n, intersected with v intersected with n. And since we have all these intersections over here, it doesn't really matter if we kind of reshuffle everything a little bit. We can put this u and this v next to each other, so we can have u intersected with v, and so this whole thing intersected with n. And as you can see, u intersected v as we showed in the other picture, this we know since u and v are elements of the original topology, this also must be an element of our topology. And since A intersected B is in the form element of the original topology, which is what we want over here, intersected with n, then A intersected B must also be in the topology but restricted to n. So we showed the second axiom. So let's do the third axiom. What does the third axiom say? It states that if we have a collection of subsets C alpha that are already in the restricted topology, then this implies that if we take the union over all these alphas of C alpha, this must also be in this restricted topology. So how do we show this? Let's assume there's some C alpha in this restricted topology. So by our construction, there exists some U alpha that's associated to each of these C alphas in our original topology, such that if we take the intersection of this U alpha and our subset N, this recovers our C alpha. So now let's see what happens if we take the union over all these C alphas. So the union over alpha of C alpha, well, we know this is the union over alpha. Now C alpha, we can write it as U alpha intersect N. So here's U alpha intersected N. And how can we simplify this? What we can do is we can actually pull this intersection with n onto the outside. And I believe this is one of De Morgan's laws, actually. You can probably look that up if you want a proof. But we can write this as the union over all these alphas of U alpha intersected with n. And intuitively, this kind of makes sense. You can draw a picture to convince yourself as well. But this is what we have now. And now we use the axioms of topology again, and notice that since U alpha, we assumed it to be in the original topology, then the union over all these U alphas must also be in the topology. So this whole guy over here, this is an element of our original topology. And since we've expressed this subset over here as element of original topology intersected with n, this implies that the union over all these alphas of C alpha is indeed in the restricted topology. So we've just showed that this restricted topology to n is indeed a topology. So now we can use these for a couple of nice examples. So the first example is actually for a circle. So what does a circle look like? Well, it's just some shape that looks like this. That's actually too much at the moment. This is just topology, so a circle is just some closed loop like so, and we want to be able to put some kind of topology on this. Now what we can do is that notice that a circle is simply just this closed loop but embedded in the plane R2. So here's my plane R2. And what I'm going to do is I'm going to fit a circle onto this. Now, how do we put a topology on this circle? Well, we know there's already a topology on R2, namely the standard topology. So what we can do is take R2 with the standard topology. And what's one way to describe this closed loop? Well, let's call this S1 over here. This is actually how you describe the circle as a set. You just call it S1. A one-dimensional sphere, if you have a sphere, then this would be called S2 and so on. So these are just some names that you might see quite often. So S1, one way you could define this as a set is just the set of all points x, y in R2, such that x squared plus y squared is equal to 1. This is one possible way you could define S1. And now what we're going to do is, since this is just a subset of R2, so S1, this is a subset of R2, we can take the topology in R2 and put it onto S1. So if you take any arbitrary neighborhood or open set in R2, let's say this one over here, then notice what is the intersection with S1. It's simply kind of like an interval on S1, but the ends are not included. So this is an arc on the circle that doesn't contain its boundary. And in fact, you can do this with all the topologies and so on. For some subsets, it might not actually intersect with the circle. So in fact, the intersection there is empty, but that's fine because empty set is always part of the topology. And if you take a set that includes the whole entire S1, then the whole entire S1 is of course part of the topology. So yeah, the topology on S1, that's just the set of all these little intervals over here that don't contain the boundary on S1. Of course, you can take the union of them together and yeah, whatsoever. You can actually never get closed intervals on S1 because in order to get closed intervals, then you must be able to find some neighborhood in R2 that would actually include these points in the boundary somehow. So maybe you would need some closed set or something like that, but we know that's definitely not in the topology. Nor can you construct an element of the S1 topology that only contains a single point, because yeah, how do you even get this point? If you take the intersection of some subset that's kind of very close to the edge, well, you're always going to get some kind of open interval over here, and no matter how small you switch that, well, it's eventually going to become just an open empty set or something like that. So you can never recover anything that contains the boundary in the topology. So that's the topology on S1. You can also construct the topology on the integers as well. So for example, you could have tau standard but restricted to the integers. So what would that look like? Well, you have your set of integers over here, and what you do is you take any arbitrary neighborhood, I guess, and just take the intersection with the integers, and you'll actually recover each of these points over here, and you can make these open intervals as big as you want, and you'll just recover more of them. And in fact, the standard topology restricted to the integers, I'm pretty sure this is the usual topology that's people use on the integers, if that's even ever useful. That is the discrete topology. So this is the power set of the integers. And maybe one more interesting example is when you have the real line, but let's say we don't want the real line, we only want a particular portion, let's say from 0 to 1. So let's say this is our set n, for instance. Then how do you construct a topology on 0 to 1? By inducing the topology from the standard topology in R. Well, you just take any arbitrary open set, so this guy is an element of the standard topology, and you take the intersection with n. But notice a weird thing happens. You actually get this kind of half-open interval, and this, by our construction of this subset topology, this is an element of the standard topology, but restricted to the interval 0, 1. So in fact, this we wouldn't usually call open in the usual topology or the standard topology, but if we have this certain restriction, then this set over here, this half-open interval with one closed n, is actually an open set. So this goes back to the idea that open sets are only defined when you have a topology. So if I give you some subset of some bigger sets, and I asked if this is open or not, then that makes absolutely no sense, because where's the topology? It's kind of like the same for vector spaces as well. If I gave you this thing over here and asked you if this is a vector or not, well, you would have no clue if that's a vector, because, well, where's the vector space? You need the vector space in order to start talking about if something is a vector or not. So back to this example, you can actually make any closed interval on the real line closed just by defining that whole entire interval as the subsets you're restricting to. So for instance, this 0 to 1 is definitely an open set because the whole entire set must be included in the topology. So you can make these funny things where you can say this guy over here, this is an open interval because, well, here's my choice of topology and so on. I'm actually not too sure if you can construct a topology in a way such that if you have this open interval, if that's able to be called a closed interval, and maybe I'll leave that as a bit of homework if you want to try to prove or disprove that it's possible to construct a subset of the real numbers in a way such that you can call this guy a closed interval. And you have to use a definition of a closed set and whatnot for that. So those are just some examples of topologies using the subspace topology, quite a useful construction. So that's all for today. Hope you guys enjoyed, and until the next one, have a wonderful day, and I'll see you guys in the next one.